to our next speaker, Stefan Hoyer, who comes to us from the Climate Corporation, where he builds statistical models for weather and climate forecasting. He's also a frequent contributor to the Python stack and is a core developer of the library Pandas. And so he's going to talk to us about making netCDF joyful. So welcome.
Thank you. All right, let's moment of truth here. All right. Let's see if I can. Oops. One moment here. I can figure out how to mirror displays. Great. This percent. And that was not the right button. Great, there we go. Okay, so I'm here to talk to you about a Python library that I've been working on for about the past year with a few of my colleagues from Climate. So I thought I would begin by telling you a little bit about myself and what we do at the Climate Corporation. So in a nutshell, it's precision agriculture powered by data science to help farmers make decisions. Things like how much fertilizer to put on their field, and that takes a lot of different types of science. But a big part of that is weather and climate science, and that's the area in which I work in. We also have a lot of agronomists, a lot of software engineers who put a nice, slick web interface on it, and so forth. But that's what we do at Climate. I am one of the scientists on the team that works with weather data. There are about maybe a dozen of us or so. All right. So what is Xray? So Xray is a Python package for working with data like in a netCDF file, and I'll go into that in a lot more detail. But in brief, one distinguishing feature is that we try to make it's a sort of a domain agnostic tool. So it's not just for people who know and like netCDF files or sort of weather and climate scientists, but I'm trying to kind of bring the netCDF data model to other scientists also, people who don't know they need netCDF. So the emphasis is a little different there than some other tools, but fortunately there's a pretty large sort of common set of sort of a common data model that works well across a few different domains. Okay, so what can you do with Xray? Why should you be excited about it? So it has tools for easily reading, writing, and transforming data that looks like a netCDF. It has an in-memory representation of a netCDF file that you can pass around between different functions in Python without writing things out to disk. Unlike tools like NumPy, Xray makes really good use of labels. So everything you can specify instead of saying that I want to access element number 10 along the third axis of this array, I can say I want to access the time that corresponds to this particular date along the time axis. So we make use of labels to make things easier to use. So another aspect is that Xray is based off of the design of a package called Pandas. Let me do a quick survey. Who here has used Python before? Great. Who here has used Pandas? Okay, that's actually a pretty good showing. A little more than I expected. So Pandas is a package for doing data analysis in Python that's actually, I think these days, is actually becoming more popular in certain communities even than the base NumPy package. It has some really convenient, and I'll talk a little more about why you should be excited about Pandas. But in brief, it's fast and has a pretty convenient interface. And both those things we try to copy in Xray. And the last thing that you might be excited about is that integrating with some other tools, we've recently been able to make Xray work on data sets that are larger that can fit in memory on your laptop. So that I'm going to call it medium data. We're not really, I don't think we're anywhere close to dealing with big data yet. Medium data is kind of the data that fits on your hard drive but not in memory. Big data would be like you need a whole giant cluster of machines to process. That's pretty hard, but at least maybe we can make some progress in that direction. Okay, so briefly, this is what an example Xray dataset looks like. If you're familiar with netCDF, and I think most of you probably are familiar with netCDF, it's very similar just to the model of just being a netCDF file. Is a data model. You have a whole bunch of multidimensional arrays. They have labeled axes, and you can also store. You can sort of toss in arbitrary metadata associated with each variable. So it's a relatively well-formed structure. It's a whole bunch of arrays of data lying in the same coordinate system, and that shared coordinate system makes it possible to do a lot of these like label-aware operations. All right. Let's see here. Great. Okay, so I'll give my pitch for Pandas and why you should be excited about Pandas and not just as another tool for doing your computation. And this was really a large part of the motivation for me with Xray is I saw this library Pandas that makes a lot of things, data analysis tasks, really easy. And I thought, why can't I do this for netCDF? So Pandas, the main object in Pandas is a data frame. So if you've used R, this is what the statisticians know and love, the data frame. It's similar to an Excel spreadsheet where you have a bunch of, so my example here on the right, I have 4 different columns, A, B, C, D, and they have, and each of them has a different type of variable, and then I also have, in this case, I have row labels as well that correspond to dates. But the nice thing about data frames is they keep all your data aligned in one place, and they're an object that you can easily manipulate and keep your data all aligned together. They have a lot of really nice features, things like making use of labels, so you don't have to use arbitrary numbers. You can use names for things. Names are great. People can remember names. We have this grouped operations, which also show some examples a little bit later, but things like I want to group I want to take the average of the average temperature grouped by, say, like date, for example, in my data set would be a group by operation. And then it has a number of other features that are very convenient for working with data, but especially the other aspect that I really like about Pandas is that there's a growing ecosystem, sort of domain, and it's not across a variety of domains for working with data in Pandas, as well as these other Python libraries. And so it's really great to have access to those libraries and to be able to use those easily with data from netCDF. So kind of try to bridge to use the entire ecosystem together. So let me give a quick preview of what you can do with Xray, or at least sort of an example of what we can do today, and then some things could be a little bit easier. But so one thing, so we can open up a data set, which could be a whole bunch of files, netCDF files sitting on disk. That's the top here. And we'll open that up, and they'll be sort of all combined into a large virtual data set. Then we can do something like, so in weather and climate science, we do a lot of calculating climatologies. So that's just the average by the time of year for a variable. So we might group by the month part of, so the calendar month out of the year, and take the average over time. That's our climatology. And then we can calculate the anomalies, which are the difference from the climatology, with just another line as well, to take the difference for each month of the year from the climatology. So these are this is a very sort of weather data specific sort of analysis you might do, but the machinery here is actually entirely domain agnostic. And there are a lot of other interesting things you can do with these sort of grouped operations that work across domains. And then we might do things like, you want to analyze your data, you want to make a couple of plots. This is a little, we'll select out, say, a particular latitude longitude point, and sort of the nearest point in the domain to that. We'll convert it over into Pandas, which has some nice functions for plotting things. We'll plot it, and then we might use a library like matplotlib to plot an image as well. Say, again, a specific subset of the data. Then we're done. We just write it all out, the anomalies, which we'll write out to a netCDF file, and it will have all all of that original metadata will be intact. So we don't have to rewrite the labels. We don't have to sort of keep track of that separately. All that information is automatically maintained along with our data objects. So that is sort of the promise. We'll see how well it works for you. So I wanted to mention one other thing before I open up my demo and we start sort of the more hands-on part. So there's this. So one sort of big deal in climate science is conventions and how to deal with metadata. So I imagine how many of you are familiar with CF conventions? All right, how many of your data sets always follow CF conventions? Great. So conventions are wonderful in that they sort of encourage you to use a relatively standard way of organizing your data. But in the real world, it's really hard to follow like a very long list of rules for exactly how to organize your data sets. And if you try hard enough, eventually usually you come up with something that doesn't fit well even. It's not always possible even to follow the conventions. So our approach here has been, we do want to follow some of these, and we want the ones that we can usefully transform into a data model. So if we have something, for example, if the conventions tell us how to label points along an axis, and that's a thing you'd want to do in your script, we'd like to make use of the conventions and read it into our data model. But if there are other conventions that we don't quite know how to handle, so for example, if there's a convention that lets you put in, say, some sort of arbitrary text, for example, for say maybe we don't know an xray, we don't know how to deal with cell bounds, for example, which would be like the start and the end of a cell. We don't really have a nice way to make use of that. So supporting that directly wouldn't make anyone's life easier. So we sort of don't directly support those. If you want to deal with, there's sort of a long tail of conventions that if you want to deal with that, you're going to have to maintain that metadata yourself. You can do it, and we won't stop you from doing that, but we're not going to directly support it. And that's the same thing is true. I guess one big example of that would be units. I know keeping track of units is a really convenient thing to do. And there are some nice Python packages that make that relatively easy. None of them have, at least my experience, has been, I have not found the trade-off of using them to be worth it yet. So we don't directly incorporate those in Xray. Okay, so now we can try to do this, try to open up your laptop. I'm going to sort of work through some examples that you can follow along. So this is on the Unidata Workshop site. And let me see if we can, let me see if I can point you guys in the right direction. One moment. Okay. Let's see here. Make this full screen. Okay. Have you guys found have you found the GitHub page for the workshop yet? Great. So if you browse the notebooks, you'll see there's the Xray tutorial here. So you can download this. I think actually maybe the easiest way to download is if you go on my link to the notebook viewer website, and you click here, Xray tutorial. There's a big download link up here. Click on that button. You can download that notebook. Let's see if I can get everyone to open up that. Maybe put a green sticker on if you've successfully launched the notebook from the. I'll note we had a. You launch it from the Xray environment. So source activate workshop Xray, and then we'll do IPython notebook. Maybe I can show you guys what that looks like. One moment here. So you've done. So I'm going to type source activate workshop Xray. Go into my downloads folder here, and I'm going to start a IPython. Just type IPython notebook. And you can see all the stuff in my downloads directory. That would be how would you click it? How would you open it up? So once you're, I guess maybe the zip file would have been a good idea. All right, maybe put a red sticker up if you're still, there's something you're trying to figure out still. All right, if you have this notebook open, I'm going to make this bigger so we can actually read it. Let's see here. Down here. All right. Okay, so I'm gonna try to get started. If you're still struggling, maybe put up a red sticky note, and someone can one of the helpers can come around and try to find it. Or we'll have a break in a little bit when I can show you. Yeah. Not necessarily. So Xray does not necessarily. So what I'm going to show you guys today mostly is going to be Xray reading things into memory, but I'll show you a little bit at the end what it looks like when you're not reading everything into memory. Usually it reads things into memory when you sort of access the data. So, yes, that is definitely the hope. Yeah. Okay. So let me go ahead and get started here. The first thing to click, there's a link here for, well, so we're going to start off by running this first cell just does some standard imports for Python. Then the next thing we're going to do is we're going to do a little bit of data analysis with this netCDF file. And you click on that link, and depending on how many people are simultaneously clicking on that link at once, it will download pretty quickly, hopefully. And you'll have that sitting in your downloads directory. So if you want to follow along with my example here, you should be able to. The next step here would be simply type in the path of that file in that file that you've downloaded. I'll make that a little more readable there. Okay. A little tricky to get the pacing right here. All right, so I'll probably sort of get started here, and then we can go back and deal with some of this when we go to the first exercise. So what I have here is just a single netCDF file with some weather data. In this case, it's from an NSEP reanalysis. We can take a look at this data set, and we'll see we'll see what we're working with here. It's relatively small, but 25 by 50 by 3,000 roughly. And this is a grid, and there's one variable here, and it's called air, and that's an air temperature. So we have an air temperature on a two-dimensional grid. In this case, it's for over 2 years of data. We'll see in a minute here. It's the start of this data set is in 2013. And it goes from 2013 through 2014. The latitude and longitude coordinates here are over North America. All right. So the dataset object here is a lot like a netCDF file. This is our in-memory representation of netCDF file. When you access the dataset.air, that pulls out a particular array from that netCDF file. So that gives you something that works like a labeled NumPy array that has labels for the coordinates, and it has that metadata as well. So depending upon whether you want to work the whole file of data or just the one variable, you can do that. The abstraction here is an xray dataset is similar to a Python dictionary of these data array objects, and this is similar to in Pandas, where the data frame is like again works like a dictionary of like one-dimensional arrays for each column. So we can do things like do Python dictionary like things like look up what are the keys of this data set, which are going to be the names of each variable. We can check if a variable is in the data set. We can do things like there are 2 ways to pull out a variable from data set. You can use the dictionary like syntax with square brackets, or you can use the attribute style with the dot. And the dot one works really nicely for autocomplete in IPython. So you can do dataset dot and then do a tab to complete a variable name. So we can look things up 2 ways. Inspect some of the metadata on this. We have dimensions. Those are, in this case, just a map from the names of each dimension to the size of the dimension. So your data set, like a netCDF file, every variable on the latitude dimension has to have the same number of elements. That's the restriction. And we also can look up the attributes here, which is simply a Python ordered dictionary, which stores each element of which stores each of these metadata elements. So we can go ahead and add in, say, we'll add in an element here. I'm going to add in a foo element, a foo attribute, and give it the value bar. And if we look back in the data set, print it out, we'll see that it has a new piece of metadata that we just added to it. We can, for an individual array, we can pull out the dot values gives us just a normal unlabeled NumPy array. So that's useful for sort of working with the rest of the NumPy ecosystem. And then we can pull out little pieces of a few different pieces of metadata for the array as well. We can pull out a list of the dimensions with which it's associated. We can pull out the attributes. We can pull out the shape of the array. This is again like the NumPy-like attributes, and we can pull out that metadata. So so we have the 2 objects. One's like a dictionary. One is sort of like an array. And now I guess we'll start off with sort of something simple here. We'll say we can just if we have things working properly, we can save this data set back to disk. And we discover that it's not. Let's try restarting this notebook. I'll run this again. Yeah, absolutely. Yeah.
The values access there.
Yep.
So you are not doing master arrays?
That's a great question about master arrays. So I am not. Yeah. So the xray data model, I do not. NumPy has that notion of master array, and so the approach that I take is sort of modeled off the approach that's used in Pandas, which is that instead of using a master array, we use the not a number floating point value for missing values. So it's a little bit of a hack. Master arrays don't have great support in the Python ecosystem. Obviously not a number is not necessarily the same thing as a missing value, but it sort of works. It has similar semantics. Yeah, so that is the approach we take. That means that makes a lot of operations significantly more efficient. But it is a little.
So you're subbing in names for.
Yep. Yes. So it appears that I may have a bug here. That's yeah. Mm-hmm.
Second here is netCDF 3 Classic.
Yep.
Does this work with netCDF
It does work with netCDF4, yes. So we have a few different ways to read and write netCDF files. We can use the official Python netCDF4 library. We can also use the SciPy library. Let's see if that works. Yeah, okay. Well, it's not, for some reason I screwed something up with my example data set here, and it is not writing out, which is a little unfortunate right now. I did have it working earlier. Yeah. There we go. So apparently I changed it to netCDF4. Take out the classic. All right. So apparently I accidentally added some netCDF4 feature in here or something like that. I'm not quite sure what I did there. Yeah. So the sort of subtle distinctions between the different variations of the netCDF formats. netCDF, I think there's a 64-bit version of netCDF3 that. Yeah, so I borrowed the names from the netCDF Python library.
Well, there's netCDF4 class.
Yes.
I don't think there is. I think that
Is that right? Did I put in the entirely wrong name? That would. Well, okay. I'm not quite sure what I did there. I did something that so changes to netCDF4. You can write it out to a data set, and you can look at it in your if you have like NC dump installed, for example. You can pull that up and you can read out, verify that all the metadata was still there. So that's just reading and writing an array. So I want to show a couple examples of things of so what can we actually do with this data set? So we can do things for pulling out data. Sort of again, when we have these arrays, we can, similar to what you can do with NumPy, if you provide some integers, you can just directly pull out, say, integer by position, take out the first element or the last element, or some range of elements, the first three elements. Now we can also do that by label now as well. And here we leverage the machinery in Pandas, which makes it very efficient to look things up by labels. It's essentially just, at least algorithmically, it uses a hash table, so it's really fast to look up things by label. We can pull up, say, everything corresponding to that first timestamp along the first axis. And we can also do things with name dimensions as well. So here's what I mentioned earlier. We can say, take the time dimension and pull out the first value by label. And we can actually use a string, even though it's internally represented as a datetime object. There's Pandas has sort of a shortcut that lets you specify something as a string and translates it into a date for index lookups. Yep. Sorry? Yes. Yes. So generally, it does need to be some part of an ISO 8601 string. It doesn't necessarily need to be the whole thing. So you're allowed to say cut off the dates, and you can just get the month, and it will give you, say, 124 values in that first month, or 1,400 values in that year. But it needs to be basically like an ISO date string. Mm-hmm. Yep, it also works for latitude and longitude as well. The difference is that there you have to know the order of the dimensions. So I have to know if I wanted to do longitude, that's the third axis, and so I have to look up something. I can say pull out every latitude at a particular longitude of 200. So this is the. Yes, the string is a convenient way to look to. Yeah, for that long you put up numerics. We also have a shortcut I can show you for looking up nearest locations as well. So here's again usually I recommend using this dot select syntax to pull out things along name dimensions. That lets you not worry about the order of your dimensions in your array. That's one of the joyful parts of Xray is that you don't have to worry about the order of all your dimensions, which if you've used NumPy with high dimensional tensors can be a real source of pain in my experience. So you can pull out things. Unfortunately, due to the limitations of Python syntax, we can't put this in square brackets. So when normally what you'd write with a colon in Python, you have to actually create a slice object directly. So the syntax is not quite perfect. We might try to convince the Python developers that they need to change Python to make that easier. That's a bit of a tough sell sometimes, but I think that may be able to happen sometime in the future, hopefully in time for everyone to use Python 3. So you can do things like select out a range of values, select out particular locations exactly, and we can even do things like, so if I try to look up 271, there's no location, there's no longitude 271, but if I say that, but let's say I can add a method here and say I want to look up the nearest location, and I can pull out, and it will pull out the nearest location in the original data set for that value, which is what it will select out for me there. And that's actually, in this case, you see it's 270. So that's an example of pulling things out. We'll talk a bit about computation. So what can you do with these objects? So you can compute with them just like you would with an array of data. You can do things like multiply them by some value. You can do things like you can use NumPy functions like square root, which act element-wise, and it will actually automatically it'll keep around the metadata, which is a cute trick. Unfortunately, that doesn't work yet for doing it to a data set. If I just do the whole data set, I get an error, but we can apply that element-wise to a data set. Take the square root of everything in the data set. We also have standard aggregation functions. So we can do, say, the maximum. We can take the mean along a name dimension, take the average along the time dimension. I can take the median over latitude and longitude, a couple dimensions at once. So that's the very basics of computation and selecting values with Xray. So now, yes, so between attributes and labels. So the metadata that Xray is aware of are the names of each dimension and the labels of each point along each dimension. So that would be, like, for example, if I have a time axis, each timestamp. If you have some sort of extra metadata, like let's say you add in something like we'll notice in our original data set, for example, has some metadata. It says these follow the chords conventions or the 4 times daily reanalysis, and it's from corresponds to the signal level, etc. That metadata is not preserved when you do some of these arithmetic operations. So when you try to take the average of a data set, or maybe you're taking the difference between data sets, like a lot of that, it's not always clear exactly what metadata is valid still and what's not. So we take the approach that we just sort of try to get rid of it all if it's something ambiguous. So that is sort of, again, sort of the kind of trying to do the pragmatic approach to metadata. So I have an exercise here that we can give us a try. I don't know if probably not going to get through all the exercises here, but at least I'll give you guys a try to work out a couple of examples if you manage to get the notebook working. And manage to load this data set. All right, so I will give you guys a few minutes to do that, and put up the red sticky note if you're struggling.